special pit 嗰啲之後，轉咩之？
反而佢冇講上次嗰啲 pit 打幾多 SPT 落幾少，好似冇講。有啲同學問啊，冇放啲 sample 上，唔係放個 sample
係喎，佢上次
佢放咗啦，放咗張相上。
話咩會唔米咩啊？唔記得我已經。
會唔知幾多米打幾多，跟住又話嗰個 piston 個 spacing 係同呢個，有時係攞住 spacing 嘅 mic 同嗰個，你知個能源幾厚啊嘛？佢又咁講。
後邊咪喺個咩個龍卡度。
同埋最緊要就係一定 feel 30，因為我問佢嘛，使唔使 feel 30嘅 spacing 啊？佢就話
唔使意思，即係我要10米咁樣。
即係可以數 spacing 大嘅數，佢就你只要夠多嘅話，我 section， 即係我哋都 section， 咁用 critical section 上面我覺得即係我原本跟佢，即係我已經話嘅時候，哇即係我有次踢好床啊，打著咁嘅樣咯，
嗰個 scale 即係個 scale 幾
差唔多成嗰邊啊嘛，呢啲係
係啦，幾多成幾多米嗰度？呢個咁嘅情況，400幾，即係我12成4咁樣鋪落去。
如果你睇翻嗰啲咩呢啲好易揾到嘅，係啊，呢啲
冇咩咁啱。
開實啲都唔得。
370米，係啊，100米乘40，100米乘370米。
但佢係要過咩路線咧？
咁樣
上得係要
包埋個公園咯。
係啊，過咗
去到條馬路咯，我記得。
過馬路嘅面啊？
係去到馬路咯，唔包地鐵㗎嘛。
跟住就即係我自己畫嗰陣咧，就用咗60米，60米40，跟住之後就畫咗張相，跟住就話即係當然啦，喺佢講唔同之前嗰個，
自己諗下先啦，咁講啲啊。
係啊，跟住又諗起啲事啦，去到差唔多3、4個字之後先驚到唔使呢個嘅技術。有啦，同咁啦。
大家晚上好咁咧就我哋今晚咧就繼續講呢個 hydraulic 啦上一堂課咧，我哋由呢個 hydraulic jump 就開始講起嘅。咁 hydraulic jump 咧，即係我哋喺 open channel 度呢個嘅 non-uniform flow 嘅其中一個部分啦就叫做 rapidly vary flow 嘅咁我哋主要係呢度咧係通過去分析佢嘅個 force 同埋嗰個continuity equation 同埋 energy equation 咧，去 develop 咗一條嘅 equation 係去 predict 到個 hydraulic jump 嘅嗰個 water depth 咧係可以通過呢一條 equation 咧去 estimate 出嚟嘅。咁我哋要知道嘅呢個 equation 咧，我哋需要知道係兩個參數啦，一個係 water depth 啦，即係上游嘅water depth 啦，同埋上游嘅呢個 flow number。咁 hydraulic jump 咧出現咧係需要有一個必須嘅條件嘅。上游咧係 supercritical flow， 下游係 subcritical flow 先至可以 generate 到呢個 hydraulic jump 嘅即係會係需要有咁嘅條件之下先至可以形成到。咁當呢個條件係達到咧，如果係 rectangular flow 咧 ，rectangular channel 咧就係用Y1、Y2啦。咁如果係 non-rectangular channel， 即係譬如話啲 trapezoidal 半圓形嗰啲咧，就要用hydraulic depth hydraulic depth 去計啦。OK， 即係如果係佢係 non-rectangular channel， 就需要將呢一啲參數咧換翻去嘅。另外咧 hydraulic jump 咧，我哋其實咧亦都會關注嗰個 energy loss 嘅。上堂課就冇點冇點樣講到energy 嘅 change 咧就其實就冇乜特定嘅 equation 嘅咁你就其實就最主要咧就係計翻咧兩個 delta E 嘅 difference E1 減 E2， 即係 Y1 加上 V1 嘅二次 over 2G 減去 Y2 加上 V2 嘅二次 over 2G 即係通過係計算兩個即係上游同埋下游 jump 之前同埋 jump 之後嘅嗰個 specific energy 嘅 difference 咧，去 estimate 佢嘅energy loss 係幾多嘅呢個係常見嘅一個計算方式。呢個 hydraulic jump 主要就要涉及到呢啲內容啫咁然後跟住咧就我哋亦都講解咗咧另外一類嘅non-uniform flow 咧喺 open channel 度叫做 gradually vary flow 緩慢嘅一個水面變化啦咁我哋首先 develop 咗呢條 equation 大家通常就唔會話直接用呢條 equation 嘅主要係去用我哋呢一科咧就主要係用呢條 equation 咧去解釋翻點解個水面咧會係有啲咁嘅變化嘅啫咁我哋主力咧要知道咧係有12類嘅water surface profile 其中有5種嘅 slope 5種嘅 slope。Mile slope，Mile slope 就係 Yn 大過 Yc 嘅即係個flow 係佢嘅Mile slope 並不一定代表住個 slope 係好平咁係最關鍵嘅判斷咧就係 Yn 同埋 Yc，Yn 大過 Yc 咧就叫 Mile slope。咁如果 Yn 等於 Yc 咧就係叫 critical slope咁如果 Yn 少於 Yc 咧就叫 steep slope咁然後跟住睇翻個 slope 本身係唔係平，同埋係唔係反波咧，就有 H 嘅 slope 同埋 adverse 嘅 slope 兩類嘅 slope， 所以 total 夾埋係3類嘅 slope。咁呢3類嘅 slope 咧，我哋再考慮翻呢個 actual 嘅 water depth，actual water depth 睇下佢係 屬於係邊一個檔嘅，邊一檔嘅嚇 M 幾 OK M 1 M 2 M 3定係 C 1 C 3定係 H 2 H 3即係呢啲去判斷翻佢係屬於邊一檔嘅。咁佢呢度幾張圖咧係幫助咧判斷咧，即係唔同嘅 profile 咧，佢嘅水面咧個變化嘅趨勢係會係點嘅譬如話 H 3呢個，佢係 subcritical flow、supercritical flow 但係佢個水面會不斷上升到咁上下咧，佢嘅即係佢個kinetic energy 咧係不斷轉化緊去做potential energy 嘅，去到某一個程度咧，當佢嘅呢個 Fr 咧係約等於1嘅時候咧，就會出現呢個 hydraulic jump 㗎啦，就會出現 hydraulic jump 嘅即係因為佢係我哋睇條式咧，當個分母咧接近於1嘅時候，隨住嗰個 cross section 即係個水面嘅cross section area 越嚟越大咧，佢個 velocity 會越嚟越慢嘅。本身就係 Fr 大於1嘅 supercritical。咁但係如果係當佢嘅水面係越嚟越上升嘅話咧，咁佢 Fr 咧就會越嚟越接近於1。當佢係等於1嘅時候咧，佢就會出現呢個 hydraulic jump 嘅情況，就呢條 equation 咧係 solve 唔到啦。咁所以佢係一個係個過渡喺呢個solve 唔到呢條 differential equation 嘅時候咧，就係產生緊呢個 hydraulic jump 嘅情況。咁所以咧就我哋譬如話我哋喺有啲題目咧係要大家咧去計算咧嗰個 water surface profile 嘅，計算完之後咧我哋再通過去compare 個 YNYC 啦，定佢嘅係乜嘢 slope 啦。唔同嘅 slope， 如果個題目淨係叫你畫 water surface profile 嘅，因為唔同嘅 slope 佢就即係如果唔同嘅 slope 咧，佢睇下要睇個長度嘅個長度同埋一個坡度嘅變化啦咁佢會係可能叫你去 predict 一啲 positive 嘅possible 嘅呢個 water profile 咁你可能會需要考慮唔同嘅情況下，佢會有機會出現啲乜嘢嘅 profile。咁跟住係一個咁啦，有啲題目咧。佢會俾晒一啲比較實際嘅參數嘅，咁嗰啲我哋可以完整計算到唔同嘅 location 嘅嗰個 water depth 嘅，咁去到如果係咁嘅題目咧，咁我哋畫完之後，題目又叫我哋去畫呢個 water surface profile咧，我哋就需要 mark 翻低佢究竟係邊一類嘅 slope 同埋邊一個偏途嘅即係咁樣呢度一啲嘅例子啦另外咧就我哋都講咗一個嘅 direct step method 嘅方式咧，去計算嗰個 water surface profile 或者叫做直接去計呢個 water surface 咁呢個做法咧就係我哋會 assume 呢一個嘅 water depth 通過我哋一個 control 一個已知嘅 location 嘅 water depth 去predict 啦，佢可能係上升或者下降啦咁我哋 assume 一個嘅 water depth， 跟住咧再通過 assume 嘅 water depth 咧計翻個 velocity 跟住計翻嗰啲嘅 friction slope 呢啲嘅參數OK， 咁跟住咧再代入去咧就揾翻個 delta x。如果個 delta x 計出嚟係即係用我哋 assume 嘅呢個 water depth 計出嚟嘅係正數嘅話咧。即係話我哋呢個 assume 嘅 depth 咧係喺我哋嘅 control point 嘅下游部分個 depth 係下游部分。咁如果我哋計出嚟嘅嗰個 delta x 係一個負數嘅話咧，咁即係話我哋 assume 嘅呢個 depth 咧係喺我哋個 control 嘅上游嘅部分，即係咁樣即係佢呢個嘅係一個有啲似係一啲 try 嘅方法try and error 嘅方法 ，try 出嚟究竟佢係上游。不過我哋通過water surface profile 呢12個咧，其實我哋亦都可以幫助大家知道咧，譬如話，如果假設佢係A3 profile 嘅 ，OK， 假設我哋知道佢係反波，咁係而且 supercritical Chapter 6 and 7部分嘅內容嘅。Okay? So today we will go to the new topic, the topic number 8, the applications in the pipe flow. Okay. Now in topic number 8, the applications in the pipe flow, we may mainly talking about two things. One is the pump system. Another one is the hydraulic transfer, which is also named as the water hammer. Okay. This is two very important thing in the pipe system design. Right? So because you know that in the water supply system or the water drainage system, sometimes okay, you need to use the pump to provide the energy to push the water to flow. Okay, and associating with the pump system, especially when you're considering the protecting the pump. Okay, you need to consider how to eliminate or remediate, okay, the water hammer effect when the pump is turning on and off, okay. It will be very critical consideration. Now, firstly, the pump, okay, I think that is not a very brand new thing. I think that if you are doing the engineering related to the water, you should know what is the pump, okay. Now, there are many types of a pump. Okay, but in the water supply system for the civil engineering, civil works, infrastructures, main types of pump is the several types. Okay, one of the very common pump is the centrifugal pump like this. The centrifugal pump it is named as a centrifugal. That means it uses the mechanism of the centrifugal effect.
Pumps move fluid in a straight line. Most axial pumps are located at an elbow.
A multi-stage
Hi everyone, in today's video we are going to discuss what is the component.
Now, a centrifugal pump, now actually most of the pump is mainly contributed by maybe we say the two parts. One is the motor, okay, the motor which provides the motion, the energy input. The second type is the propeller, the moving part, okay, and the shell. So that so most of the pump included these two parts, okay. You see that the motor there's nothing very special to talk about. The main design of the pump is also considering the pump's rotation speed, the motor rotation speed, and also we also focus on how the design of the pump, the blades and the flow types. Okay. Now the centrifugal pump is a kind of pump that includes that the shell. Okay, there is the direction of the flow is coming from. We call this is the pump eye. Okay, pump eye. So this one, okay, is pump eye. Is this this is where the flow comes to the water comes to the propeller, and then the propeller will rotate.
Animation, right? So what is a centrifugal pump? Centrifugal pump is a mechanical device designed to move fuel by converting rotational kinetic energy into hydraulic energy. Okay? And in industry, centrifugal pumps versus the rotating part. About the components of a centrifugal pump, so there is impeller. Impeller is the rotating part of the centrifugal pump, which rotates. You can say the impeller is the rotating part.
Now, this video shows that how the centrifugal pumps works. Okay. Now, you see that the moving part is the impeller here. The water comes from the pipe and enter the pump through the pump eyes here, okay? And then and as the rotation of the impeller, that due to the centrifugal effect, that the water will force to go in the sideway, okay? In the sideway, and then force it to go out from this direction. So this is the main mechanism of how the pump works, okay? So that you see that, so that is from the design and mechanism of this centrifugal pump. So that for the manufacturers kinds of consideration, you may need to determine how large is the size of the impeller. Okay, you may consider how is the rotational speed of the impeller, and also you may consider how much is the design of the flow. Okay, so this will be affecting the efficiency. We call it efficiency of the pump. Okay, so efficiency of the pump is talking about how much of the energy input can be reflected as output to the water flow. Right. Now, for the centrifugal pump, now you see that the flow is flowing in by the pump eye and flowing out at a direction normal to the pump eye, the axle, at the axis of the rotor. Okay, so that actually for the centrifugal pump, we also name as the radial pump. Okay, if we focus on the flow direction. Okay, if we focus on the flow direction, the in-out flow direction, we will also name this centrifugal pump as the radial flow pump. Okay, because that the flow inflow and outflow are on a perpendicular direction. Okay, on a perpendicular direction. So this is the radial flow. The figure A, the figure B are the radial flow. And the figure B, figure C. Okay, figure B is now if usually the radial flow, you see that due to it changes the direction, so that it changed quite much about the momentum, so that the work done by the impeller has been spent to change the momentum of the flow. Okay, so that sometimes the efficiency is sometimes not around 70 to 80% most of the time for the efficiency. Now, but if you want to have a higher efficiency, and if you want to pump a larger, more higher amount of the flow, you may consider that if we can, okay, spend less of energy to change the momentum. That means that the inflow, outflow direction, if they are approximately aligned, okay, so that it will make that the pump, okay, will have a higher energy efficiency, right? So that here is the we call it axial pump, okay, the axial flow, the figure D, the axial flow. And in between the radial flow and the axial flow, that there is a types of pump, but which may not be quite common. Okay, it is called a mixed flow. Okay, mixed flow. Okay, because it's not the inflow and outflow is neither perpendicular and inline. Okay, neither perpendicular nor inline, so that is called the mixed flow. Okay, these are three types of the flow, right? Radial flow, axial flow, and external flow. Now, for the pump design and the pump, or we say the pump selection, okay, because we are not the talking about the mechanical engineering, we are not manufacturing the pump, but when you are doing the calculation or engineering the pump system, you may need to select the types of pump, okay, from the supplier, okay. So you may mainly focus on two things. One is the pump capacity, which means the discharge, okay, the discharge. And another thing is the pump head, okay. One is the pump discharge, another one is the pump head. This is the two main things that you need to consider and as the kinds of parameter to select the pump. Now, usually every pump, when it is made by the manufacturer, or you find a catalog, okay, you can see that there will be the pump itself will print this some of the information of the pump body. Now, I randomly search the pump plate, okay, just like this. Okay, now, so this is types of the pump plate that is attached to the pump surface, so that you will find the information about the maximum discharge, the maximum pump head, okay. So, for example, this but usually most of the pump indicates that I think that this is a small pump, okay. Small pump, small discharge, but high pump head, okay. It can be maximum and minimum, okay. It has a range, and then minimum is 26.4 meter, and then this is 69 meter maximum. And the discharge is 30 liters per minute and 130 liters per minute. And then you can also see that what is the power, the rated power, okay, the rated power. So this is talking about that the N is the revolutions per minute, revolution per minute, all right. The working condition for the pump, 50 hertz. The revolutions per minute is the RPM, all right. You see the rotational speed for the rated rotational speed, so that it tells you many specs for the pump, okay. IP55, I think that this is the water resistant level, okay. The maximum liquid can resist is 85 degrees Celsius. So that this shows the information that you can see that you can use this for consideration of buying a pump. 1.3 kilowatts is not a very big pump, okay. Let's see that is there any other powerful one. No, nothing, okay, nothing. Now the pump that in our the lab, okay, for very it's not bad, okay. So the pump in our open channel is 3.5 kilowatt, okay. So 280 something, okay. Not sure the specs about this one. I think that this is most of the just small pump, okay. The plate showing in this search. So so that this is this shows that an example, okay. How can you find an information for the pump? Now, from the manufacturer, the pump catalog, manufacturers have catalog, there will be a kinds of a pump curve. Alright? The pump curve, you will see that mainly that the vertical direction, vertical axis is the in the unit of meter, which means that this stands for, this is a pump head, okay? This is pump head, the maximum pump head, okay? And this is the discharge, or the capacity. Alright? Now, the pump head, the pump curve is usually in this manner. It's a reverse proportional relationship, okay? So, so this is the, this end indicates that the maximum pump head. This is one of the, now you see that this is types of the model. I think that this stands for types of model, okay? But usually the pump curve is, I think this is a range. That is, for example, of this, one of the pump curve, it can say that the pump can work on 0.5 to 1 meters pump head and can provide the 0.5 to 2 meters cube per hours flow, okay? So that this indicates that the range of the performance of the pump, like here, okay? So, so that you see that if you want to have a higher discharge, usually you will, the pump can just provide a less pump head, okay? If you want the pump to pump the water into a higher location, that the discharge will be not that large, okay? So that the better range for using the pump is in usually in the middle range, okay, to have higher efficiency. Some of the figures, some of the catalog will also provide you, okay, the now this is another type of pump pump plate. That this one is 7.5 kilowatt, okay. It's relatively a larger pump, okay. Now, we mainly focus on the capacity and the head of the pump can provide. Now, let's see that a very simple pump system. Drawing the water from a lower reservoir to a higher reservoir. Okay, so most of the pump, okay, you may we will later talk about another thing is talking about which is the cavitation. Okay, now for the pump system, for installing the pump system, you need to consider the cavitation effect. Okay, the cavitation is a kind of the phenomenon that generate many air bubble, or may not say the air bubble, the hydrogen bubble, not the vapor bubble. Okay, so it will be damaging the pump impeller. Okay, so this is a typical pump system setup. That this is a lower reservoir, and the pump is installed here, and this is the suction side. Okay, this is the suction side. And this is the downstream, or we say the after the pump eye. This is the downstream, or the working part. Okay, to the second upper reservoir. Okay, so from the point of view of the energy grid line, you can see that the pump will provide a pump head. The pump head to overcome the steady head and the dynamic head, and then to let the flow provide to the second reservoir. Okay. Now, for the suction side, there is elevation between the water surface of this lower reservoir and the pump line. Okay, this is a CS. HLENT indicates that the entrance head loss. Entrance head loss. Entrance head loss. This part, okay, other than the entrance head loss, the HLM and the sum of the HLM indicates that the pipe head loss and the minor loss. For example, there may be the valves, the bends in the suction side. It indicates that the drop here, the drop of the head here indicates that the loss in the suction side. Okay. And the downstream includes that the loss in the pipe system, okay, in the downstream. So this is the typical pump system, okay. Now, for just now we have shown you that there are from the flow direction of the pump we classify it as the three types: the radial flow, axial flow, and mixed flow. Okay, I have found some video to see that what's the kinds of the different types of the flow looks like.
In the piping system, a drive shaft extends into the process flow with a propeller attached to the end. When the propeller turns, the blades pull the fluid down the shaft.
Now the axial flow usually indicates that the immediate flow direction is not perpendicular to the flow, but there may be another setup in this is more it's not quite significant. The impellers, the motor's direction is the propeller. The impeller is here, okay, and the immediately outflow from passing the impeller naturally is this propeller type, and then it is direction the same as the inflow, okay, but it turns another direction after the propeller, so that usually this kind of pump can provide a very significant flow rate, okay? But usually it is not able to provide a very strong pump head, okay? Now another classification of the pipes, the pump, okay, maybe focusing on the stage of the pumps, okay, to fulfill some purpose. Now, you see that the axial flow pump, okay, can provide large discharge but less pump head, okay. So that some of the design will increase that the impeller number, okay, to produce a large flow and also the higher pump head by inserting more propeller here, okay, so that this is so-called the multi-stage pump, okay. This multi-stage pump can be usually found in the pump station, okay, especially for the pump stations to pump the water from the ground, or sometimes that to raise the water, okay.
Centrifugal.
This is a horizontal multi-stage
at a
pump.
much higher discharge pressure by using two or more impellers. The main components of a multi-stage centrifugal pump consist of the following: the casing, shaft, impellers, bearing housing, the driver, volute chambers, suction port, and discharge port. The pump casing is the body of the pump and contains the shaft and impellers. The casing provides shaft-bearing housing.
We don't need to focus on a very detailed, components, but we know that the multi-stage pump is a type of pumps that with multi numbers of the impeller, so that it will be able to increase that pump head, this is horizontal type, and there is another vertical type.
This pipe, newly designed impeller.
So that the vertical type, is able to raise that the water from deeper location, raise it to a higher elevation. So this is as consideration of the flow direction. Now, actually, the multi-stage pump can increase that the efficiency of the pump, because they have some of the energy is lost, for the single stage pump, because there is the flow, the turbulence generated in one motor, one propeller, but if there is multi-stage pump, they can sometimes increase that the efficiency, energy efficiency. Another types of pumps that may be very usually used in some we say that the wastewater treatment works, or pumping that the so-called drainage water, irrigation water, especially for those water that may not be very clean, as the fresh water, the drinking water, So those kinds of water usually considered using the screw pump, screw pump. The screw pump is not using the centrifugal effect. It is using the just like let the water take in an escalator, and then to climb up the pump blade, and then to make it to just take in the ladder and then go to the upper location. So this is usually used in the locations that which is usually it is to pump the water that with not that clean situation. So that you see that the water is gradually move up, to the higher location according to this effect. So for the centrifugal pump, common centrifugal pump, you see that the gap between the shell, the casing, and the impeller is very narrow. If there is big stuff, the clogging, it is very easily to damage the pump, the centrifugal pump. So that in some scenario, it will be using this kinds of the screw pump to transfer the water. And for example, in Hong Kong, we have previously visited Now, we previously visited many sewage treatment plant. They have used the screw pump to raise the wastewater. And we also visit the stormwater storage tank, rural stormwater storage tank. Also, it uses this screw pump. The screw pump has the advantages that it is very less chance to be damaged. Because they are not easy to get a clogging. that the screw pump is not that easy to get damaged. Okay. Now there is after we talk about the pumps that we will introduce, that's some pumps parameter. One of the these are the parameters. We say that the operating characteristics, the discharge coefficient, head coefficient, and the power coefficient. Okay. For the same, for talking about if the pump, the propeller is the same, okay, the size of the impeller is the same, that these coefficients are the same, okay. So they check so that it means that the discharge will be proportional to the rotational speed, and the head will be proportional to the power 2 of the rotational speed, and power will be the cubit of the rotational speed. So that for the same pump, that means the same propeller or impeller, all right? The coefficients of the pump is the same. So this for the coefficient, discharge coefficient, head coefficient, and the power coefficient. You can see that the discharge is proportional to the power 1 of the N is rotational speed, okay? The H is the pump head is proportional to the power 2 of the rotational speed, and the P, the power, is the same power 3 of the rotational speed. Okay. So this affinity laws is talking about that if the pump, propeller, impeller has the same diameter, that the discharge head power ratio is the same as the ratio of the corresponding rotational speed. Okay, so that's what I mean. The power is the discharge is power 1 of the N. The head is power 2 of the N. Okay, the power P is cubit of the N. All right. For previously we have introduced that different flow types of the centrifugal pump. Okay. Now there is radial flow, mixed flow, and the axial flow. And how can we select the correct or appropriate type of the flow to fulfill our purpose? Okay. Now we can calculate a parameter which is called the NS, the specific speed. The specific speed, NS. NS is calculations of the discharge coefficients over the head coefficient. Okay, and the final equation is NQ power 1/2 over the head 3/4. Okay. For example, if we design that the pump will be used to deliver the discharge of some level, some amount, and to raise the water to a certain level, okay? We can calculate the specific speed. The specific speed we will combine with this figure, okay? Now there is an SI unit and the US customary unit calculation. Now the SI unit, the number is referred to the number here. Okay, the U.S. customary unit talking about the gallon day food system. Okay, or gallon mini food system. See, gallon day food or gallon mini food system. Okay, it's supposed to be the because it's the dimensionless. Okay, it's dimensionless. But the Q and H, all right, here, okay. I think that is gallon day mini system, okay. Gallon day mini system, and this is the SIU system. That means using the meter and the second and or kg, this kind of calculation, okay. So that for different types of the number, for example, if you calculate that the specific speed is 50 for SI unit, so you look up, okay, you look up here and look down here, okay, so that this 50 fall into the range of the mixed flow. So that you will consider that if the specific speed is equal to 50, it is better to select the mixed flow type, and then look out here, okay, if your discharge is, for example, like 31.5 approximately, this discharge, so that you will see that your estimated discharge efficiency, the pump efficiency will be around, if you are using this pump, this kind of pump, the efficiency will be around 77%, okay, around this efficiency. So this figure it helps you to select appropriate types of pump, and you can use these kinds of pump to estimate what is the efficiencies that you will have around for that kind of pump, right? So this is the use of the specific speed. Now here we are going to introduce a phenomenon talking about the cavitation. Now the cavitations of the pump is not because of now you see that the cavitation. Now here is a video that's showing that there is an impeller, okay, and rotates in inside the water, okay. You see that the strip here, this one, it's like the air bubble, okay, it's like the air bubble. Seems that this propeller is already submerged in the water. There is no sources for the air bubble, alright? I can tell you this is not the air, this is the vapor, okay? Strictly speaking, this is the vapor, it's not the air, okay? 咁呢啲你見到呢啲嘅泡泡咧，唔係氣泡嚟嘅，係嚴格嚟講係蒸氣泡 ，OK？ 佢都係 gas， 但係佢唔係 air， 佢唔係喺上，唔係喺水面打入嚟嘅啲空氣，佢係點解會咁咧？So it is because that the blade move at a very fast speed. Actually, we have explained previously a little bit, okay? According to the Bernoulli equation, you know that the Bernoulli equation tells us that the P over gamma plus elevation plus V squared over 2G equal to a constant, right? Now, supposedly at the same location, that the elevation is not changed. If fluid moving speed is increased, then there must be a drop in the pressure. Okay, so that if flow moving speed is very fast, that means the pressure will be dropped down, maybe having a negative pressure. Negative pressure means that the pressure is lower than the atmospheric pressure. Okay. And you can also see that from the vapor pressure of the water, okay? The vapor pressure of water is like, now the vapor pressure of water is like a train of, it's something like this way, okay? It's something like this way, okay? Maybe we find the reference. Now, here it shows that the vapor pressure of water. Alright, now you see that for the pressure, now this is 1 kPa, 10 kPa, 100 kPa. 100 kPa is 1 atmospheric pressure, 1 atm, alright? 1 atm. Now if it is lower than 1 atm, for example, if now is 10 kPa, 1/10 of the atm, that the pressure, that the temperature for the boiling is lower than 50 degrees, okay? If, for example, 10 kPa situation, that the pressure for becoming the boiling, okay, of water is lower than 50 degrees, okay? 即係話，如果佢嘅氣壓係低嘅時候咧，個壓強係低嘅時候咧，佢嘅水滾嘅温度咧，我哋平時100度嘅水咧，係喺講緊咧係一個大氣壓嘅情況下咧，100 kPa 咧，101咁上下啦。咁佢係對應係100cc度嘅一個水滾温度，即係我哋要將個水煲到去100度咧，佢先至滾嘅。即係水滾嘅意思即係佢變咗蒸氣啦，係咪？變咗氣化嘅。咁但係如果我哋啲 pressure 細到某個程度咧，譬如話佢10個 kPa 啦，咁佢咧就40度就開始水滾㗎咯，即係咁樣咯。Okay? So that means if the velocity is fast enough, that making that the pressure drop down to a certain very low level, for example 2 kPa, that or maybe less than 10, okay, 5 kPa, so that the water may get a boiling from about 20 degrees Celsius. So that you can see in this figure, in this video, this is another video, okay, showing that. Now, in this video, the gases is not generated due to the entering of the air from the water surface. It's generated, okay, due to the rotor, okay, due to the rotor. So that this is generated due to the movement very fast speed, okay, of the for the propeller, okay, moving at very fast speed. So generating vapor is not the thing to damage the propeller, okay. But you see that here near the edge of the blade is low pressure, but leaving the blade, okay, when the bubble leaving the blade, it becomes a higher pressure, okay. Then at the edge of the propeller has a low pressure generating the vapor, but leaving this, it will become a higher pressure again for the water nearby, okay. So that the bubble will clash, okay. 離開咗呢啲嘅線葉嘅呢個邊緣嘅時候咧，佢就開始會去到一個相對高壓嘅地方，咁佢就會爆開啦。咁爆開嘅時候 ，OK， 一個泡泡爆就冇乜嘢嘅。但係大家如果飲汽水嘅時候咧，如果啲汽水喺你條脷嗰度咧爆開咧，你就會 feel 到咧有啲嘅衝擊力，係咪？咁所以呢個好硬嘅嘢咧，佢呢度有可能成千上萬個 bubble 㗎啦。咁佢喺咁嘅情況下爆開咧，咁日久即係時間耐咗咧，就會對呢個會造成一啲嘅我哋叫做 cavitation 嘅 effect 啦。So it's like this, okay? When the bubble collects, it will generate a very significant shock force, okay, to the blade itself. This is another point of view for the generation of this the gas bubble, okay, the vapor bubble due to the low pressure generation. Now this is the gearbox, okay.
佢咩糖蝦嗰個頸
Now this is another video typically talking about that power generator near the propeller. Alright, so this is the so-called the cavitation. Okay, the cavitation will damage the impeller. So that's for the head for the design the water pump. Okay, the pump station. We need to calculate a thing. Okay, to see that we need to calculate some parameter to see that whether the pump setup is correct. To eliminate those the pump cavitation effect. Okay, then we will calculate that the available net positive suction head NPSHA, and then at the eye of the impeller that then compare to the required net positive suction head NPSHR. Okay, so. This can be referred to this figure, okay, for the suction side. Yeah. Calculate up to this propeller eye, okay. Now, so that why that we will usually not suggest that. For example, if you are going to pump the water to a higher reservoir, the recommended setup is like this. Okay, the pump eyes is lower than the water surface. Okay, the lower the better. Okay, so it is not suggest that you set up the pump on the surface to suck the water up. Okay, to suck the water up and then pump to the higher location. It is not quite suggest to do like this, okay, unless you have no choice, okay. It's not suggest to do this because this will have this is easy to have a negative net positive suction head, okay. The net positive suction head is calculated by the PATM over gamma. This is the absolute the pressure head, absolute pressure head, absolute ATM pressure head. ZS is the elevation, the difference of the lower reservoir surface to the pump eye. Okay, this one, this location, ZS. Okay, the difference of the level between the low reservoir surface to the pump eyes. Okay. This is usually a positive number, okay? And then PV over gamma. PV is the vapor pressure at the certain air pressure condition, okay? It should be referred to this figure. Okay, you can find if necessary, okay? It is just like in this here, okay? Usually one for this temperature, okay, so it's 100 kPa, okay. The vapor pressure head, and then the HLENT, the entrance head loss, and the HLF maybe in the suction side there is a pump valve or other components, okay. There may be the expansion or maybe the pipe bands, and HLM is the this is the pipe head loss, okay, pipe head loss, friction. This is the minor loss, okay, comes from the components but fittings in the suction side, okay. So you will compare that the NPSHA and with the NPSHR, the required, the actual or the available, and compare with the required suction head. Okay. Now this is usually provided by the spec or the catalog. Okay, from the pump menu. Okay, so that's you will need to consider to calculate. This NPSHA is from your setup the manual. Okay, you may need to have the MPSHA larger than this one. Okay, to ensure that the pump will have less chance to appear the cavitation. Okay. Now, another one is the calculations of the Thomas cavitation constant by dividing the cavitation inception over the the total dynamic head per stage. Okay, if it is a single stage, the total dynamic head is talking about this one. Total dynamic head is talking about the from the pump eyes to the secondary reservoir surface. Okay, this is the total dynamic head. Okay, total dynamic head. That means the pump head, okay, need to provide to overcome the head loss in the downstream and also the elevation difference. And for another calculations that the Thomas cavitation constant can be determined by this way, okay? The K times NS power 4/3. The K can be found in this figure, okay? The K value can be found in this figure. The K value is suggested for different pump efficiency that the pump is working on. For SI unit and US customary unit, okay? So that the MPSHI can be therefore is calculated by H. H is the pump dynamic head. K is the parameter from this figure, the table. NS is the specific speed. Okay, so that you can calculate the MPSHI. That's MPSHI is the cavitation inception. That means if the net positive suction head, if it is lower than this value, it will appear the cavitation. Okay. 如果呢個 MPSHA 係低過呢個嘅話咧，就會係出現呢個 cavitation 嘅情況啦。OK， 即係咁樣去諗呢樣嘢。OK， 咁 MPSHR 咧就係個 manual， 即係可能你有啲嘅 design standard 就要求你嗰個 MPSHA 咧係要大過呢個嘅，所以咧MPSHR 咧係會應該係高過呢個cavitation inception 嘅，即係佢會有啲 safety factor， 你係一定要大過，即係你個available 嘅 suction head 咧要大於呢個係至少㗎啦嚇，咁攞翻多啲 safety 嘅嗰個room 咧就要更加攞大少少嘅，OK， 所以喺啲 menu 度咧會可能就會 indicate，OK， 有個個 MPSHR 係要去到幾多嘅。
喺嗰個圖嗰度咧，會唔會睇到嗰個嘅MPSHA 大概係邊個？定係冇
？MPSHA 喺呢個圖上面咧，佢咪呢個 ZS 加埋呢一個嘅 PATM， 即係呢個嘅 level 啦，即係呢個高度減去呢一個，再減去呢個嘅
有寫咗嗰度。
咁所以咧剩低嘅就係 MPSHA 就係 available 呢個嘅。咁如果假設減完之後呢兩個減完之後咧，個 MPSHA 咧係變咗係即係可能調翻轉啦，佢呢個好大嘅 head loss 嘅，假設好大 head loss， 即係如果出現有咁嘅情況咧，個 head loss 好大嘅，佢會可能會低過呢個嘅話咧，咁就大鑊啦，咁就會出現呢個 cavitation 啦。即係個 MPSHA 係一個負數嘅，即係負數嘅，咁即係低過呢個 PV pressure head 嘅呢嚿嘢嘅，即係呢個嘅 vapor pressure head 嘅，咁你就可能會出現一個叫做 cavitation 嘅現象。
啱啱抖一抖神咧，嗰個 PV 係 air 嗰個嘅
vapor pressure， vapor pressure 嘅。 pressure 可以查到嘅。
OK。
Okay. Now, but this is just for information. We are not mainly calculate these things, okay, for the pump system. But we focus more on how to select the pump and design the pump combination, okay? Because sometimes that you, for a water supply system, it is not just one pump, okay? There may be multiple pumps. Now, the pump, come back to the pump curve, okay? Pump curve. The pump characteristic curve, okay? Or we say the pump curve. It is a curve that provided by, by the manufacturer. This depends on the size of the pump. Okay, depends on the size of the pump diameter, and also the rotational speed. Okay, and also according to the rotational speed of the motor. Okay. And then, so that this is figures that list out that the pump on different diameter and running on different status, okay? Now, the horizontal is the capacity, the maximum discharge. The vertical is the total, the maximum head, all right? So that is usually arranged in this direction, okay? So the number here talking about the efficiency. So that we see that most of the higher efficiency location ranging in here. Okay. Now usually for the single stage pump, this is talking about single stage. That means one impeller. Okay, one impeller only. Usually running on 70 to 80%. It's seldom higher than 55%. Okay. Now, when this figure shows that when a pump is applied to a kind of the pump system. Okay. Now, because you know that from the suction side, there may be the head loss due to the entrance, due to the head loss due to the entrance, due to the friction from the suction side, and due to the minor loss from the suction side. Okay, so that there is the head loss, the head drop in the suction pump. Okay, we say that the station loss. Okay, that it calculate this part of the head loss. Calculate that in the pumping station. Okay. The head loss in the pumping station. Out of the pumping station is the head loss due to the water supply system. Okay, so this counts that the loss from the pumping station. Now the head loss is usually proportional. The head loss is usually proportional to the power 2 of the discharge. Okay, the head loss is proportional to the Q power 2, okay? So that you see that if the discharge is providing larger discharge, that the gap, the actual or the modified pump curve. The modified pump curve is that the actual performance for the pump after subtracting that the head loss from the pumping station, okay? So that this solid line may be the pump curve that's from the manufacturer. Okay, you buy the pump. Okay, you see the catalog. When the pump is a brand new pump, that it may produce the performance like this solid line, but because you put a pump in a pumping station, you need to consider that the head loss due to the piping and the entrance. Okay, and maybe other fittings, so that there is a loss in different discharge situation. So you will load this performance down to provide a modified pump curve. Okay, because this depends on the pumping station piping setup itself. Okay, so the manufacturer cannot predict this for you. Okay. So here the statement talking about that this head is called a shut-off head because this maximum head is appear when it is at zero discharge. But zero discharge, that means it's not appear the head actually. So that this is called the shut-off head. Now the figure here, okay, the figure here shows that the same diameter of the pump and running on different rotational speed, okay, different RPM, revolutions per minute, okay, so that with the higher revolution, that the pump curve like shifting up, okay, shifting up, and this curve shows that for the motor is running on the same speed, but as the diameter increase, that the performance is shifting up as well. Okay. Now, I'd like to ask. Okay. Now, these are this curve in the bottom, two graphs in the bottom, is one in the pump in series. Pump in series means that there is an in series pump like this. This is in series. And pump in parallel, okay?呢兩個 graph 咧分別係一個 in series 同埋in parallel 嘅 pump 嘅 ，OK？ 咁大家估下邊一張圖咧係 pump in series， 邊一張圖係 pump in parallel？ 大家估一估，大家根據你嘅理解，即係同 discharge 同埋 head 嘅嗰個，即係如果兩個 pump 夾埋一齊嘅話，佢會係點樣嘅一個情況咧？係睇下，即係你覺得邊一個圖係講緊 pump in series， 邊個圖係講緊pump in parallel 嘅？
左邊 parallel， 右邊 series， 我覺得調翻轉。
OK， 就係有唔同意見。OK， 有同學話左邊第一個，即係我哋講有同學就認為呢個係 pump in parallel， 亦都有同學認為呢個 pump in series 嘅，係啊。
因為頭先講過話，一個泵佢嗰個俾嗰個 head 係有限嘅，或者係連住泵，即係 in series 你個 head 你先會有得提升咁樣。
係。咁
所以左邊個 case exactly 就係話你in parallel 個 case 你個 head 係定咗嘅，但係咧你可以 double 個泵，你就會 double 個 discharge。係
OK， 係啦，你嘅分析好啱嘅，係啦，冇錯。嗱，咁我哋都係從呢個 head 同埋個 discharge 去睇啦嚇。咁 in series 嘅話咧，佢哋兩個泵咧係即係同一條線上面噶嘛。咁佢哋唔會有兩個 discharge 噶嘛。咁我哋加啲輔助線就知㗎啦。OK。咁譬如話我哋喺呢度同一個即係同一個 head 嘅時候咧，咁樣打橫一條線落嚟咧，同一個 head 嘅話咧，當你一個泵嘅時候咧，一個泵嘅時候佢即係話即係譬如話你淨係開一條線路咧。即係呢度咧，我哋從呢個 parallel system， 即係 pi system 都大概知㗎啦。呢個 parallel pi system 咧，佢哋 head loss 咧，佢哋 total head 咧係一樣嘅，即係兩條線路係一樣㗎。咁就同一個 head 嘅情況下咧，當你有一個泵去開着嘅時候咧，佢就最多去到呢個 discharge 啦。如果你兩個泵着埋咧，佢個 discharge 係可以加大嘅嚇，即係咁樣。同一個 head， 佢呢個 pump in parallel 咧係令到個 head 有明顯變化嘅 ，OK。咁但係個 discharge 咧就會係根據你開幾多個泵咧就會加大咗嘅，咁pump in series 咧就因為佢係一條線路嘅，一個 in 一個 out 嘅，所以個 discharge 咧係一致嘅。咁我哋譬如話我哋呢度有對條線上嚟睇啦，咁當我哋一個泵去 operate 嘅時候咧。即係假設即係個泵個即係淨係開一個嘅話咧，咁佢就淨係 produce 到 provide 拉到一個比較細嘅 head。咁如果我哋要即係加大個 head 嘅話，可能去抽去好高嘅地方。咁我哋可能即係呢啲叫做通常就係一個中轉站嘅一個咁樣啦即係如果我哋要即係去一個非常之高嘅地方，一個好高嘅山嘅，咁我哋喺山腰嘅咧會再加一個嘅booster 嘅一個泵啦。咁所以就加大個 head 嘅，即係咁樣去睇啦。咁樣所以係咁樣判斷咧有邊個係邊一條係即係 parallel 咧，邊一條係 in series。咁所以咧左邊呢個咧係 parallel 嘅。Okay. Yeah. So the analysis is very good. Okay. Now, so that for the so that we see that the pump system, okay, we are not just talking about a single pump. So maybe there is multiple pumps, so that you may need to use the parallel and the series arrangement to fulfill the purpose of your design. Okay. So here is talking about the pump power calculation. This equation is for the U.S. customary unit for the CFS in the discharge and pump head in foot and the discharge in the weight, specific weight of water is pound per cubic feet. E is the efficiency, no unit, okay? So that the equation there is a coefficient of 550. For SI unit, the power, brake horsepower is actually the power, okay? Is calculated in gamma QH, okay, which is the same as the thing we talked about in the pipe flow. The gamma is the specific weight, 9810. Q is meter cube per second. H is the meter, all right, in the SI unit, right? Now, because that's so that's in some this curve also talk about that the range of the pump that running, okay, for the different rotational speed, and for the same motor, different diameter of the blade, okay. Now, for the system head, system curve, we call the system curve. Now, previously we talked about the pump characteristic curve. We talked about the pump itself, okay. The system curve is the curve that talking about that the system requirement for the pump for this system, okay. For example, if we would like to deliver the water from the lower reservoir to the high reservoir, okay, at least we need to overcome. We need to so that it will be a curve like this way. It will be a proportional curve other than the pump curve, okay. So it indicates that if you want to pump the water for a larger discharge, you need to provide more pump head, okay. So this one is called a static head for the pumping downstream. Static head uses the same head as the previous suction pump, okay. Seems that it's a little bit confusing. Now, total static head means that the elevation difference of the lower and upper reservoir, okay? Because that the pump you apply to this system, at least, okay, to overcome this static head, you can make the flow happen. Okay, this is not considering the frictional loss, other things, okay? The frictional loss and the component head loss, for example, the pipe and the fittings, will be proportional to the discharge, to the flow velocity, okay? So that higher than the steady head, if you pump the flow faster, okay, so you need to overcome more frictional and the component head loss, okay? So that the typical system curve is like this. Now there is also, this is not quite common, okay? The source reservoir is higher than the terminal reservoir, okay? It's not quite common, okay? But for some purpose to increase the discharge, maybe that happen, okay? So this will have a negative steady head, negative steady head, okay? But the dynamic head pump is the same, is also proportional. This is not quite common, okay? Now this is, the bottom one is the system with two different discharge head, with two receiving reservoir, okay? With two receiving reservoir here. That means if you use one pump, okay, to provide the head to pump the water, if the head is just reaching this level, okay, the ZS1, only reach the ZS1. Now because you can adjust that the rotational speed of the pump actually to control the pump's working status. So that if you just want to pump the water to this reservoir, you only need to turn the pump working at this the head near this head, okay? So that you can control that only the pump only pumps to this reservoir. But if you want to pump the water to this and at the same time the both reservoir, okay, you need to at least provide the pump head as large as here, okay, to overcome that the head difference between the second receiving reservoir to the source reservoir, okay. So that you will need to there is two receiving reservoir situation, okay. That if that happen, okay, the same head profile that can have the two the additional discharge, okay. You will have this kinds of the requirement, okay, the system requirement. That means system requirement. This figure shows that the variation of the system requirement for the receiving reservoirs level change, okay? Because that as you pump that water to the receiving reservoir, that the water level will increase, okay? That the water level will increase. That so that when the receiving reservoirs level increase, that the pump head is also increase that, okay? This figure shows that for the system curve that by adjusting the head loss, okay, varying the loss situation in the flow system, okay, that will produce a different system head requirement, okay. So usually this is for the head loss. The head loss, if it is larger, that means it makes that the system curve will be steeper, okay。即係呢度有個呢個圖咧就講緊，如果譬如話你有個水掣去 control 嗰個批嘅head loss 嘅話咧，咁你個 system curve 咧會係咁樣 shift 佢呢邊嘅，去彎佢變得更加 steep 嘅嚇，即係話你要俾到你個同樣一個 head 咧，你個 discharge 會變細啦，即係同樣一個 head 你個 discharge 變細，或者你同樣一個 discharge 咧。你會需要更大嘅 pump head 去先至令到個 flow 咧去 happen。Okay? So the thing is, we need to combine the pump curve and the system curve to find the intersection, to find its system operation point. The system operating point indicates that, okay, you apply this pump in this system. It will work on the status of the discharge here and the head here, okay? Because we know that the pump can provide the head range, okay, like this, and discharge range as here, okay? But if you apply to this system, you have a known, okay, or can be determined the pump working status, okay, just like this. Now, maybe we may take a break first, and then we will come back later to talk about something.